Okay, so right now we finished last class with our experiment. So this data set, I'm gonna pretty much give you an additional layer to this analysis of this data set. So Tyson, for instance, mentioned what happens if you have a data set which is mostly rational, but then there is 1 point out of the 50, right, that fails rationality. Then what do we do? So in the previous class, I told you about measurement error, but today I'm going to tell you about something called goodness of fit, right? So again, the idea is going to be very simple. It's going to be about trying to have a notion of errors again in the model, but in this class of models characterized by the generalization of reveal preference. Okay, so we're going to introduce something that is called the Afriat's cost efficiency index, and it is a measure of rationality or rationality performance, right? So suppose we have a data set that cannot be rationalized by any U. So in other words, guard fails, right? What does it mean? That from the 50 observations, there is a chain of observations that create a strong cycle, right? So at some point, have X1 indirectly will prefer to Xn, and then finally Xn is strongly and directly will prefer to X1. So I have a violation of guard or SARP, right? And now what can I do, right? So one option, different from the measurement error option, is to say, look, so maybe I don't want to throw away rationality if people are very close to maximizing. So how can I define the notion of misoptimization, or trying to make small mistakes? Well, we can add what is called an Afriat efficiency index. And this is going to be given by a modification of the budget set, okay? So in particular, I'm going to define now, and this is something I'm going to write right now, right? Let me do this here. So I'm going to use this alpha in the following way. So let me define an E number, right, between 0 and 1. Let's use the alpha, right, between 0 and 1. And right now I'm going to let 1 be included. Later I'm going to change it. And now have the following way, right? So I have PT PT is going to be multiplied as usual by the XT, right? And then this is going to be greater than PT prime XS. And here I'm going to add this alpha value. And then I'm going to define this even only...
Sorry, is it possible to move the mouse cursor that's on it? It's kind of hard to see what's going on there.
Okay.
Oh, yeah, perfect. Thank you.
Can you see it better now?
Yes, that's perfect. Yeah.
Okay. Okay, and this is basically I'm going to define the new reveal preference relation called R alpha. Directly will prefer to access. Okay. Everyone gets this definition? So basically what I'm going to say is that I'm going to declare fix an alpha, right? For instance, fix alpha equal to 1. And then this is equal to the traditional direct reveal preference relation, right? Alpha equal to 1 is the standard one. But now, what happens, for instance, if I let alpha be equal to 1/2? Now, right, this relation is going to be smaller because some XT are not going to be reveal prefer anymore according to the 1/2 modifier. So you're going to kill some reveal preference relations, right?
So
yep.
Higher the value of alpha, the more efficient it is. Like that's what we
exactly. So if you are, so this is it's going to be interpreted in a bit. I'm going to tell you that interpretation of alpha is kind of the fraction of income you, as a consumer, are wasting by picking something that is more expensive but will give you the same utility. So it's wasted income. So 1 minus alpha. So when alpha is equal to 1, there is no waste, so full efficiency. And when alpha is equal to 0, it's full waste, right? So you are wasting your money, you are not maximizing, okay? So I'm going to tell you the interpretation in a second. So, but right now the notion that I want you to get is that alpha 1 is rationality, right? And alpha 0 is someone that is doing something crazy, because when alpha is 0, then nothing is revealed preferred to anything. I don't get any information, right? So what does it mean? So it is about the strength of the revelation. So before, right, we just said, it's an ordinal comparison. We say, if something is peak, xt is peak. When xs is affordable at price is pt, I declare xt will prefer to xs. Now it's about intensity, right? Because I have this alpha. So if when alpha is 1/2, for instance, I'm taking the ptxt, which is the amount of income, and dividing it by 2, right? So I have 100 tokens, now it's 50. So now only if this 50 value, right, is greater than or equal than ptxs, then I declare prefer xt to xs. So in other words, xs has to actually be really, really cheap, right, in comparison with xt. So now how cheap you are matters. So the intensity matters, okay? Good. So what is the idea? So imagine right now, for instance, that I have a data set that fails rationality. And in particular, I observe that x1 is revealed preferred directly to x2. x2 is revealed preferred directly and strictly to x1. So this is a violation of work, right? Now, what do I do? So imagine then the rest of my data set is fine, right? So pretty much, if I take the data set, the data set here, and then pretty much remove from this the elements here, p1, x1, right? Then basically this thing satisfies GARP. Right? So what I'm saying is that by removing any of these two observations, I remove the only cycle in this possible data set, and then I'm back to GARP. Okay? So this data set is like Tyson set. So there is only one mistake, right? So only one cycle. Let's do x1 is revealed preferred to x1, x2, and then x2 is strictly preferred to x1. And that means that, and when I remove any of these observations, then I'm back to rationality, okay? So now, well, how do I account how bad the rationality is? Of course, one measure would be to how many observations do I have to drop out, right, to get rationality. That's one measure that people use. And then you divide the number of observations divided by the total of observations. So in this case, would be 1/50, right? That's a number, and it's between 0 and 1. So that's one measure called the HM, Hoodman Max. But the one that we're studying today is the Alfred Efficiency Index. So how do I do it? So another way would be to basically define now alpha in order to eliminate this violation, okay? So in particular, notice that every data set, right, will satisfy GARP, right, for an alpha relation for some alpha. Why? Because you notice that always you can take, of course, 0 to be the alpha, and then every data set satisfies GARP. Why? Because there is no revelation, right? So it turns out that the empty reveal preference relation is actually a cyclic, right? So just check the definition. So nothing is revealed to anything, right? Therefore, the premise is satisfied, is always false. So therefore, the conclusion is always true. So this is a typical vacuously satisfied, okay? So the empty relation is always satisfied. So in other words, when nothing is revealed, then of course you can construct any utility function, okay? Got it? So now that's not really interesting. What I want to find is what is the maximum alpha, right? Such that the data set here, as you can see, is going to satisfy the GARP. So my objective now is that find the sup. This is basically the big one, alpha, such that basically matcal, the data set O, right, satisfies GARP on the relation R alpha. Okay. So in other words, I'm going to find the highest efficiency compatible with GARP. Got it? Okay. So that's it. Now, so in particular, this measure, again, if you are rational, it's going to be 1. If you are completely non-rational, it's going to be 0. And then it's going to be a continuous, right? Now, that's one way to do it, right? And it's just modifying the real preference relations. Now, another way to do it is basically trying to modify, instead of trying to modify the real preference, we have to modify the budgets, right? So how do I do it? Well, basically, I'm going to take the budget, the original budget, and then change the income, right? But it's still, so...
Quick question, sorry.
Yeah.
So what's this SUP is for?
Supremo. So it's so the Supremo, right? So that's the lowest upper bound. So okay. You take all the possible upper bounds and then you take the Supremo. Okay. The minimum over that, the infimum. So again, so the Supremum here is defined because I was defining one open, right? So it's a non-closed set, right? So you have to take the sup. If I allow 1, so it's going to be closed, and you can take the max. So we can change it to max, I guess. Let's just do a max. Okay, so let me change it all to 0, 1. Good. So the second way to define the same object is by means of the budgets, right? So take the budget and now modify the budget by the alpha, right? So here, instead of trying to think in terms of trying to maximize the same utility, but now modifying the budget. So now if I try to optimize a utility function on this modified budget, then I get back to rationality. So I'm killing some of the options. So here the budgets become linear. So again, so I'm gonna just simplify the definition. So the cost efficiency index, as you can see, is basically the maximum of this alpha, where alpha belongs to this set A, which is basically the set of items that rationalize the data, right? And so this amounts to checking SARP or GARP for a grid of values alpha, such that the maximum level that is compatible with rationality is the number CI. Okay, so again, so this alpha here is going to be the fraction of people that are going to be exactly rational. So this is the data set for the experiment with 2 goods, 94 students, 2 goods. And then you can see here in the x-axis, the efficiency number, right? From 0 to 1. And then in the vertical axis, we have the percentage of subjects in the experiment that have a value of the alpha greater than equal than the particular CCI that I fixed on the x-axis, okay? So this is the percentage of people that are above this level. So let's see one example. So fix 1, so fully rational, and see the red line now. The other one, we're gonna ignore it. So the red line is around what fraction? As you can see, is around the 17% that we mentioned, right? So that's the value of people that are passing GARP exactly. Okay, 17%, around that. Now, why do we do this? So of course, rationality, when you say at face value, only 17% of the individuals pass, is a very low number, right? So you say the minority by far passes GARP, the majority fails it. So the model is very bad. But now, allow this small perturbation to the model, this alpha, value. And now imagine, for instance, that the efficiency level is around 90%. Okay, so follow the cursor here, 90%. What is the fraction of people that now have efficiency index greater than or equal to 90%? So you go in the red line and then go here is 80%, right? So 80% of the population have already an supposedly high efficiency index, right? So they are wasting 10% of the income somehow. That's the interpretation. It's just this is not formal, right? This is an interpretation of this measure that is more for intuition. It's not really a formal thing.
So sorry, Victor, basically like what you're saying is like 80% of, say, the sample is 90% rational. Is that kind of what it says?
It has 90% efficiency.
Efficiency, yeah.
Right.
So that's where you get like the 10% loss of, or you're not allocating that 10% of income properly,
yeah,
I guess.
So here is actually comparable because it's the experiment. So everyone receives 100 tokens, right? So they're wasting 10 tokens.
10, yeah.
Yeah. So
Perfect,
now
thanks.
I think the exchange rate, I forgot exchange rate, but I think the 100 tokens were trying to be mapped to kind of a minimum wage in the US. So the time, I think the minimum wage was actually low, was around $8 or something like that. So you might say that they're wasting around $1, something like that, right? So a little bit less than that. And now, so it's up to you to decide whether that's good or bad, right? It's a complete decision. So a little bit the issue here is that this measure, of course, gives you some nuance to our claims, but at the same time are hard to interpret, right? Because first of all, this measure, of course, by definition is basically a kind of a weird measure. So we create this real preference relation with alpha, which basically makes this thing is killing some reveal preference relations, right? And it's killing the ones that are not very intense. So basically it means that I have killed all the reveal preference relations that are basically with intensity higher than 90%, right? I'm keeping the rest. And so in terms of observations, it might actually be killing some of them, right? So, so around $1 difference. And okay, so now the question here is, so does this mean that rationality is good? So how can I know, right? Because what is the benchmark somehow? You see? So these guys in this paper, what they try to do is that, so in the dotted line, what they do is they say, okay, let's imagine an agent that is not intelligent at all, right? So this agent is just a machine that picks from the budget line something at random with uniform distribution, okay? So imagine the segment here in the budget line has a uniform distribution over it, right? And then you just pick at random with a realization, and you do that in each iteration. So now take that randomly generated data and now compute guard and then compute the alpha guard, okay? So the efficiency index for that simulated data with uniform choice. So it's called a stochastic choice. And if you do that, now nobody is gonna pass rationality exactly, right? Okay. But look at the people that pass around 90%, almost nobody, right? And then to get actually the level of 80%, you have to actually get to the 50% efficiency index. So the benchmark, this helps with the benchmark, right? Because you have a fully non-intelligent agent, zero intelligent agent that now is applied to the same methodology and needs 50% efficiency index to be able to be around the same level, 80%. Okay? So that's the analysis what they do. I don't think it's a crazy thing to do, but basically shows this weakness of the real preference analysis I was mentioning, that, you know, when you have a parametric model, so imagine a curve or a line that passes through the choices points, right? Then if you imagine there is some mistake in the form of some additive perturbation, like in econometrics, then you can try to minimize this OLS, right? So that notion is very well understood for parametric models. So we have some sort of perturbation to our model, and then we try to minimize this perturbation.
Victor, sorry, I'm very confused about how was this GARP simulated? Where did that come from?
Yeah, so as I mentioned,
so this red GARP is the data, right? So simulated GARP comes from some sort of model, I'm guessing.
Simulated GARP, well, basically it's a misnomer, right? But what I mean by that is you take pretty much each budget.
Okay.
And then with uniform distribution, you pick one point on the segment. So this is two-dimensional. So each budget is just a segment. So this is a segment between this point and this point. So you put a uniform distribution, and then you're gonna fall in one point in the segment. So you do that 50 times at random. So this is full random choice, right?
Oh, okay. It's completely random. Okay.
Yeah. So
within the budget line.
Yeah, this I do for all the budgets in every individual in the experiment. So we have 94. So for each individual, there is a sequence of prices. I take the prices, I take the segment, I choose the uniform choice. Okay. I do that for individual 1. I do that for individual 2, individual 3, and so on. Okay. I take the CAI and take the average, right? So this is the object here. So this is a fraction. Yep.
The gap between these two, the simulated GARP and GARP, the gap. So what does it represent, the gap between these two?
There is no really meaning. You can give it a meaning, right? You can say this is kind of a normalized success rate, right? Some people do that. So you say, imagine, for instance, you take the 90% benchmark, right? So here, how much people above the uniform row is actually above this level. Well, 90% is still at 0, right? So it's a whole bunch. But now what about 80%? So 80% is around 90%, but here you have 5%. So it's not really, the full success is not really 90%, but rather 85, right? And so on. So these people interpret
Professor.
Yep.
So just to look at the graph again. So if we look at the red line going from alpha 1 to 0.9,
yep.
We go to, you're saying 80% rationality, correct?
Yeah, 80% of individuals have an efficiency above or equal to that.
Okay, and so you're saying we lose efficiency by decreasing this alpha, correct?
Yeah. So when alpha goes to 0, you are fully non-rational. So this is a guy that basically provides no revelation. So it's completely random, right?
Okay.
Yeah.
Thank you.
So the interesting thing here is that in the dotted line, right, you're seeing, so if you are this robot, right, picking uniform points in the segments, then you may pass rationality by pure chance, right? And in fact, right, as you can see, around with a 50% level of efficiency index, you have a 80% of the robots passing rationality, right? But when the test is fully efficient, nobody passes, right? So the kind of teaching is that, a robot with uniform choice, zero intelligent robot, will never pass the full test, right? But as I relax the test with the alpha going to 0, the robot has a higher chance to pass, right? And in fact, around 20% alpha, then all robots pass, right? You see?
Yes.
So your main aim is to don't minimize that much so much. So make alpha as high as possible, right? So that everybody passes the GARP, right? That's what you're trying to get at, right?
Yeah, exactly. So we are looking for the maximum alpha that gives you the GARP on the modified real performance relation. Okay. So if you have a rational guy, is 1, right? Okay, so this is the same idea as minimizing OLS, right? So I have a mistake, right? And I try to minimize it. So here, by picking the highest efficiency, I'm trying to minimize error, right?
I have a quick question.
Sure.
So if we're looking for the highest possible alpha that makes this pass GARP, then at least according to the red line here, would we need to go with 0.6? Or is there different weighting that we can place on alpha for different population?
You say individual alphas for each individual?
Sorry?
Yeah, I didn't get that part. So your question?
Because like, okay, so basically there's like 80, or with a point 9 efficiency, there's like 80% of the
Correct.
population, right, that has that. But if we want like the entire population to
Okay, good point.
GARP, then we would need a much lower alpha.
Yeah, that's a great point, right? So imagine that my null is that everyone is rational, right? Right, because that's what we're assuming in econ anyway, right? It's not that there are a fraction of people that are rational, it's that everyone's rational, at least formally, right? If we actually are under that more stringent hypothesis, then you actually need an alpha of 60, right? So 0.6, right? So which is way closer to the robots, right? So yeah, in any case, for the 60, the robots pass around half the time. So you're still doing better than the robot in the sense that, so people are way more systematic than just random robots. That's what this is telling you, right? And so in that sense, the dotted line helps you to tell you, how good you are. But yeah, if you're under the null that everyone should pass GARP, then of course, this point here, the 0.6 is the correct measure. So I really like the questions you ask, because the issue here is that this is not, a set in stone object, right? So I want you to know this is kind of new science. So the original thing by Afriad is old, right? But the issue with Afriad is that it's a deterministic object. So in real life, data sets are not perfect. Why they are not perfect? Well, I mentioned the previous class. The main reason is measurement error, right? But also you can argue, and this is more philosophical, and here I have more doubts whether this is good or not, but a lot of people do it, hence I'm presenting this to you, is that another thing you may say is that you still want to use the utility maximization model as long as people are not far from it, in the sense that if you make optimization mistakes, the optimization mistakes are not large. So this is a kind of a different paradigm for the measurement error paradigm, because in the measurement error paradigm, individuals that are still rational, but the observer, the econometrician, the theorist doesn't see the correct data, right? You see noisy data. So therefore you take out the noise and then you're back to rationality. Here instead, you're actually allowing the model to be not a perfect description of the data, right? And you're assuming the data still to be perfect. So what you're saying here is instead, look, humans are imperfect, right? So they will never be able to optimize correctly, right? So they will only be able to be close to optimization. So I still want to use the model, right? As long as this optimization wedge is small enough, right? So that's kind of the idea. Now, there are some issues with this, and the salient issue I want to tell you is that this thing here is minimizing this kind of welfare wedge. So this is telling you the model is good as long as the individual doesn't lose much welfare, right, by making mistakes. But the issue is that if you're an econometrician, right, you are hired by Amazon, then maybe the object of interest is not really welfare of individuals, but rather being able to predict consumption of the individual, right? So as opposed to the typical OLS where you're minimizing the distance towards predictions of quantities of demand, right? That's the OLS in the world of demands, right? You're minimizing the distance of predicted demand to the real data. Here instead, you're minimizing the welfare losses of the individual, right? So what happens here is that sometimes high alphas may be compatible with huge errors in terms of prediction, right? So you use the utility maximization for people that are close to optimization, but their demands are actually very far from actual predicted demand, you see? So I think that's the main issue here. So most people are not interested in the welfare measure, right? Sometimes you are, but in many cases, you are actually interested in quantities, predicting quantities. And if so, the Afriad efficiency index is not really targeting that object, right? It's not really targeting minimizing the predictions mistakes in terms of quantities. So a lot to be done on this regard. And one important thing, as you can see from this data, is that it's a little bit unclear whether rationality is a good model or not, because it's very arbitrary. So if you pick, for instance, the protocol and say, look, I say rationality is good because at 90% efficiency, 80% of people are above the CCCI of 0.9, then, you know, I say rationality is good. And that's what some papers claim. But as some of you also mentioned, maybe I want everyone to pass, and then the value is 60, right? So, which is not great. So that's why in our paper with Nail, we instead take this more econometrics approach to the problem and say, look, so let's test still the model in the perfect data, which is data we will get if we had a perfect experiment, right? And what are the barriers for having a perfect experiment? As I mentioned, in this kind of experiments with a graphical device, there are two main issues. The first one is called trembling hand, right? So I use my mouse, I'm trying to pick over this budget, and then, you know, I make small mistakes. So maybe I want to pick this middle point, and I end up picking a little bit above, a little bit below, right? So this is a trembling hand error. And the misperception error, which is the second kind of error, is actually that I try to maximize my utility, but they don't give me the information about prices. They just give me the slope as a drawing, right? So then I have to figure out the slope. So this one here is almost a 49-degree line, right? So the ratio between prices is 1. So that seems to be easy. But what about the others, right? So do you know exactly what is the angle, right? It's very hard to figure out. So, you know, some people may be good at it. You have a grid anyway. So you count the grid dots and you actually do that. But imagine you actually round out the grid numbers, right? So then you end up computing these relative ratio prices, you know, with some error. And sometimes because the grid is cut in half, you have above and below, right? So you also may be making errors in terms of prices. So what I mentioned is that because of these two sources of errors, then you know, testing rationality in the original data, in the raw data, becomes impossible. So then what do? Instead of testing rationality individually, we can test rationality in the panel data set. So using cross-sectional variation to try to average out mistakes, right? And that's what I explained last class. So by doing so, we can then test rationality. And in fact, in our application to this kind of data, for the example of tree goods, we get that everyone is compatible with rationality, given the, you know, the 95% confidence level, because here there are noise involved. So you do a hypothesis testing, as in the class with Nail. Okay. So what is the bottom line is that at least, and more important, we also find evidence that the main source of measurement error is in fact misperception error in terms of prices. So the fact that you have this graphical representation of the slope is what makes this hard. Okay. The trembling hand is less important. It's more about trying to compute the correct ratio of prices. So we kind of give more robust evidence that in fact people are still rational in this kind of experiment, modulo the measurement error. Now, is this a perfect approach? Not necessarily, right? Because as I say here, this doesn't confirm rationality. So model, right, is only, it has two statuses, right? It has been rejected by data, or it hasn't been rejected yet, right? And then basically, you know, we go through time getting newer experiments, better methodologies, better data sets. And then, you know, if this model keeps being non-rejected, then we keep using it. Now, as Eduardo, I think, mentioned last class, with rationality, the issue is that methodologies and experiments are not perfect. So given that, you know, there is a little bit of credibility issues regarding the evidence against rationality, right? So for instance, our paper is challenging the fact that you might say that this data, if you only 12% pass the data, you're good to go. Rationality is a bad model. And then go to behavioral econ. So we say, wait a moment. So the experiment is not great. The data set still has issues. Let's actually try to test it with a new methodology that takes into account those issues. Now, is that so then, you know, the evidence against rationality dissolves, okay? Now, that doesn't mean that rationality is still a good model. It just means that the way that we're able to measure violations of rationality is not good enough, right? For instance, imagine that I do a new experiment where I remove these issues with the slopes. So there is, in fact, a new experimental device. Yoram Halevi and Lani Strill, both are Canadian researchers, and they and they created a new interface. This interface, instead of giving you the budget lines, gives you instead prices, written prices, right? So it tells you the price of this is such and such, and then actually asks you a budget allocation problem. So it gives you sliding bars. So it gives you, okay, you have 100 tokens, and now you have, say, 3 goods, and then in each row you have a sliding bar going from 0 to 100, and then here you can allocate the fraction of the budget according to the price of each good, and you will be able to allocate to good one. And then this is a budget share. And then, of course, according to the prices, you're gonna spend your total share in different things. So the sliding bars are gonna adjust to give you Walras law according to the prices, right? So it has some built-in automatization, so you will never violate the Walras law, so you're still on the budget, and you respect the prices, right? So you cannot buy more than you can. And so using the sliding bars approach, then this data set is nicer. Okay, so what do we do next? So right now I'm gonna stop the theory here. We can discuss a little bit about, kind of different experiments you can run and so on. So the first thing I'm gonna send you, like, for the next week is gonna give you this data set, actually, the 3 goods data set, and then send you a code in Julia, right? So you can run it, and then you can get yourselves these values and so on, right? And then I'm gonna send you some additional information so you can actually do the AFRED index for individuals. We're not gonna do, of course, the measurement error. That's way more complicated. If you're interested, you can read the paper with Neil and me. But that's beyond the class. So for this class, I'm just gonna give you the data set of the 3 goods, and then you can actually test rationality there, and you can learn how to do it. The code is very simple, very clean, so you will be able to do it very easily in Julia. Okay, so that's for the next class, and then you can actually play with this and understand what's going on. So the main thing here I want to tell you is that rationality is something that, if we have perfect data, we can test using the AFRED's theorem, basically in linear time. So it's super simple and computationally easy, right? This is very cool, and eventually, when we're able to get really cool, clean data and great experiments in the future, right, we will be able to apply this, and everything will be great. Now, if we have this perfect data set, then 2 things happen, right? Either rationality is a good model, right? And then you can then use these data sets to then make predictions, analyze welfare, everything non-parametrically, which is great. Or rationality won't pass. And in such case, then you need to get new models, right? You have to models of behavioral economics to add different layers of modeling to be able to explain the data. And nevertheless, this approach of revealed preference is really powerful because, as I mentioned and I highlight many times, this is a fully non-parametric approach. So it's just using the main core of the theories. So it's not giving you extra things just for simplicity. So this robust approach to rationality modeling and demand modeling is very powerful because basically you don't need to deal with parameters, right? And the final thing, right, is that there's still an open question on how to allow for mistakes and what kind of mistakes should we allow. So it's also a discussion of what kind of mistakes are allowable. So optimization mistakes, for instance, versus measurement error, right? That's basically a little bit the 2 things I think you have to start thinking. Yeah, so another thing I want to tell you is that versus this paper here, the one with the budget lines, this paper got into the American Economics Review, one of the top 5 journals, right? Best journals in the profession. So basically what they design is a very simple experiment, right? So it's almost textbook-like. So every subject gets a graphical representation of the budget line, right? And then you get to pick over that. So that seems very simple, right? What I want you to tell you is that, to get published and to get, influential in the profession, in the econ profession, you don't have to be overly complex, right? Overly mathematized, right? It's more, right now, econ is changing a lot. So it's becoming more empirical. So in this case, these guys obviously are smart, are scientists. They found a way to solve 2 issues with previous experiments. The main issue before was that it was very hard to get many data points from from people, right? So imagine when you didn't have computers and the first experiments in the 80s, in the 60s, then you actually have to give lists to people, right? And they explain the problem, they give you some prices, they give you some bundles, and then how do you pick, right? Basically, do people have to write down the budget they want, the bundle they want, right? So it seems very, very cumbersome. And for that reason, right, you end up doing almost discrete choice. So they give you choices over cars, over chocolates, and so on. And those budgets are nice, but they are too small. So sometimes rationality is going to be trivially satisfied because the problem is not complex enough, right? So those are interesting, but not the last word. But people are interested more on this kind of portfolio allocation, right? So because, you know, finance, macro, and so on. So then how do you elicit data from that? And how do you elicit a lot of data points per individual? Well, they come up with this nice graphical device. So they present each individual with these budgets. You know, this is very easy and nice to see. And then the subject will use a mouse, making the choice very fast. And therefore, you can get individual data sets of 50 observations, which is a lot, very individual, right? This is more than a lot of the time series or many data sets for countries like a decade ago, right? So have a huge data set per individual. Now, of course, there are limits to this data set. And someone mentioned in the previous class and asked me, so is there any correlation between making mistakes and the length of the experiment, right? So for instance, has anyone formally studied the probability of kind of failing GARP as more trials are given to you, right? And, you know, the answer is nobody has written a paper on that yet, but from my own analysis of this data, what people have noticed, me and other people, is that around 20 trials in, you know, the probability that the next observation makes you fail GARP increases a lot, right? So the fact that around 20 trials people get kind of bored, you know, is something that also shows the limits to this experiment, right? Because people would get just bored of the interface. So say, I'm doing the same thing already 20 times, you know, maybe I just, I don't want to do it anymore, right? So I'm gonna just start randomizing, you see? So you started from taking this problem seriously and trying to optimize something, so maybe utility, and then you switch to being random, you see? So that's an issue, of course, for the theory. So in real life, you know, in many situations, you don't have to choose as many times in sequence, right? So when you're choosing, say, an insurance product, you do it maybe once a year, right? Maybe not even once a year, maybe once in 5 years. So it's not that very frequent. So the other problem, you know, so that's error one. That may complicate things. The second error is income. So are people paid enough for doing this, right? Because in the end, you will say, you know, maybe 50, but if I pay you a lot of money, then maybe you actually take it seriously, right? The 50 of them. So imagine that the tokens, the transformation is not to the minimum wage, but rather is to big money, right? And then, you know, will these things change? So these same experimenters have done it. So they did these experiments in Africa where they kind of pay them the same, but due to the exchange rate is way more money, right? And then, you know, obviously rationality is still failing because of these issues with measurement error, but the rough rate of passing goes up. So when you have less trials, you're gonna pass a little bit more rationality, and when you have more money on the table, you're gonna pass a little bit more rationality. The issue again is because these analyses were not done taking account measurement error, we don't know really what's going on. So yeah, these are all open questions about that. But my main kind of message to you is that one kind of very rich opportunity to do research at this level, you know, next year, when you're done with this, is really come up with a nice design for doing an experiment of choice, which is clean, right? So trying to approximate to the vacuum. So how much do you pay them? How well do you pay them? But more than that, the interface. How do you make it fun, easy, you know, and allow these measurement error mistakes and perception mistakes? So still that is out there. So you have to actually solve it. And basically, it's the next question. So some of you maybe can do something about it. Yeah, but so far I think these experimenters are good, you know, are actually great. They created this nice interface that help us collect a lot of data, and this has changed a lot reveal preference. So now we can actually do empirics, right? Okay, so any question here? Any comment?
I have a question, Victor. So when you talk about all these methods that try to get cleaner data or cleaner experiments and kind of minimize the error, how do we know that these errors don't actually happen in the real life and we're kind of restricting it at the cost of decreasing the realistic aspect of it? So when you talk about income, for instance, if we actually kind of increase the incentive, how do we know that the real consumers do have enough motivation or enough incentives to really pay attention and make accurate choices?
Yeah, I mean, that's a great question. So again, but let's try to go back to the basics, right? So an experiment, right? The objective is to kind of isolate a particular instance of decision making, right? So of course we're not going to have a realistic framework, and maybe we don't want to have it, right? Because we want to really isolate all forces and try to focus on a particular thing. So for me, kind of a vacuum of benchmark of rationality would be high stakes. So it's really important. The decisions you're making are super important. And then on top of being important, the decision task is clean, right? So it's easy to understand. So there's no misperception issues. The way you collect data is clean. So there is no way I can mess up as an experimenter of trying to record your choices, right? As these surveys, for instance, it shouldn't be survey-based, right? Because it's going to be messy. Or shouldn't be self-reported. So I have to observe the choice. And, you know, and that's basically getting closer to this physics experiment, right? So you want to get as close as possible to that with humans, which is hard, right? So now, of course, humans, we also have to pass ethics review board, right? So have to be ethical. But, you know, I'm not necessarily agree with how experimenters use animals, right? That's very difficult subject because we do progress science, but, you know, animal rights. But, you know, people do experiments with animals in psychology and in neuroscience. So what they do is, for instance, one classic example of a good experiment, going to Hursana's question, right, is, for instance, this choice with frogs. So there is these frogs called Tungara frogs, and these are small frogs that they have in laboratories. And then these frogs apparently choose their mates according to their sounds, right? So what they do in the laboratory is they play a collection of sounds of real frogs, right? So I think these are male frogs, the ones that are the decision maker. And then they present to them this, or is the opposite, I forgot the gender, but nevertheless, the choices here are kind of boxes where they play the call of the other frog, right? So these are real frogs, and they just start playing to them, these different ones. So can you test rationality of the frogs? First question, given what you know. How would you test rationality of the frogs with this setup? So what are the choices, first of all, right, is the set of collection of frogs in these boxes, right? So it's a box with a song, right? So they're choosing over songs. It's a finite number of songs, right? So what do you do to test rationality? So you have to present to them with menus, right? So at least, you know, you have to give them tuples, right? Binary choice. And then, you know, hopefully you can also give them triples, okay? And then, you know, you can test their warp and garp, right? That's it, right? So that's what actually people do. So this is a famous paper, I think it's in Nature of Science. So when they actually test this for the frogs, and they find that rationality fails for frogs. And then, you know, but it's actually a big deal because biologists, they actually use the rational model. Because think about what is, for an animal, what is the highest stake decision? You know, it's actually the mating decision, right? That's kind of, you were programmed thousands of years. That's basically the evolutionary approach to biology. I'm not saying that's right, or I know it exactly, but one approach in biology is basically thinking that, you know, if there is a rational choice, should be the mating choice, right? Because you should be trying to be as efficient as possible in choosing mates, and only the efficient ones will survive somehow, right? That's kind of a story that is plausible, right? So if you're thinking of maximizing fitness, right? So think about the frog doesn't need a brain, right? So they just have the objective to reproduce more, right? So then, according to that, you know, mating different frogs with different songs will give you a chance of reproducing more often. So the fitness, this is your utility, maximizing fitness. So as you go through this rank of frogs, they are basically summarized by one number, which is the probability of getting a successful generation of new frogs, right? Fitness. So that means this is actually utility maximization, right? So you don't need to think. It's high stakes. The main thing there is that you want high fitness, so therefore it's rational choice. Okay, so if anything in the world is rational, it should be mating choice, right, for animals. But it's not. So what went wrong? So can you tell me your conjectures?
Probably the environment, because it was like a lab experiment. The environment of the experiment probably,
Well, in that case, I think so. Two things right there. So yeah, so you have frogs, right? They might not get the environment. So what they do is they kind of do a weakening of the experiment in the sense of probabilities. So they try to say, let's see if the frequencies of choice are consistent, right? So they define kind of what is called weak transitivity with probabilities. I'm going to explain that later in the stochastic choice chapter. But right now, what I want you to get is that they did allow for some error in terms of trembling hand, if you want. So the frog didn't know where to jump and so on. So yeah, imagine that's taking account, right? So that's fine. That's a good critique. But in this case, it's easy to check because given that that's the ethics part, right? So they make these frogs choose hundreds of times, So they get these super huge data sets from the frogs because they can basically make them do that every day, right? So the point being that because you have such large data sets, you can average out trembling hand mistakes. So imagine you have, the average choice, which is, this object, which is nice and it doesn't have trembling hand. So here measurement error is not of concern, but still the measurement, given that you still are not rational, right? So what is missing? So it turns out that humans are not that different from frogs. So the story turns out to be that, and this is a paper by Paul Nathanson. He is a professor in St. Louis in the Olin School of Business School. And so he wrote this nice paper, which is in another top 5 in the Journal of Political Econ. It's the only paper about frogs in the Journal of Political Econ. And he suggests basically a model of Bayesian choice. So this is a stochastic choice model. So I don't know if you have used probit and the logic, right? So this is a logit or probit model, probabilistic model, but with a Bayesian layer. So what he means is basically that frogs have limit cognition. So they actually, are not aware of all possible alternatives, and they don't understand exactly the quality. So the issue is that even if you want to maximize fitness, right, you're a frog, right? So your brain is not that complex and doesn't have much computation. So what you do is you actually map what you hear with a probability of being high fitness, right? So it's not that you know for sure this song is the best fitness possible. It's rather, I hear this song and therefore it's likely and with certain probability that you are the best, right? So we're in a world of imperfect information. And then if you take into account imperfect information, which is misperception error, right? So this the same thing I'm arguing humans also fail in this experiment. Then frogs turns out to be rational. So and that's a little bit the same message I'm giving you with this experiment and the thing we did with Nail. So once you take into account misperception error, then you're back to rationality. So right now, I mean, there is what I'm going to tell you is a speculation. So don't take it as the last word. But one kind of counterforce in behavioral econ is saying, look, it's not really about biases and people having this, these kind of saliency issues in terms of behavioral econ. If you want, some stories are about, framing and so on. It's more about everything is about attention, so on perception. So most people, most beings try to be utility maximizers, but they cannot do it simply because the perception of the world is imperfect, right? So if you were to have the correct perception of the world, you would actually maximize. So all the behavioral biases, all the violations of rationality you see in the world, human and animal, are coming due to misperception. So then what is missing in our models is modeling perception, okay?
Victor, if you did the experiments with AIs, like artificial intelligence, so would this misperception still exist? Like have these experiments been carried out with AIs?
But so what they're saying, so what you mean is that I can test GARP in choices from algorithms. That's what you mean?
Yes, yes.
Okay. So yeah, so basically that's an interesting question. So right now I'm talking about decision theory with humans or animals, right? But for instance, right now we know there is automatic trading. So you have robots making investments, right? So for instance, you can see what robots pick in terms of portfolios, right? And then you potentially can do GARP tests on that, okay? And then for instance, will the machines be utility maximizers? Well, if they are unique criterion, yes, they will be, right? If they are multi-criterion, maybe then, but then the reason of failing rationality is basically this multi-criterion versus one criterion, right? So if they have this kind of Pareto rules and some randomization. So yeah, that's a little bit beyond what we're doing now. But this is more about, you know, we're thinking about decision makers that are human or animals. So I think misperception plays a big role. Yeah, so this class, we're gonna do something about misperception, but we're not gonna go all the way. So one thing I want you to go now is in our chapters. Let me quickly go. We're gonna take now a small break until I'm gonna change now the chapter. So we have 5 minutes. So let me pause. Okay, so right now the next chapter I'm gonna, as I told you, so I'm gonna change a little bit the order of some things. This year we're going to do way more emphasis on the choice part, right? So previously in previous year I actually left this chapter as an addendum, right? The behavioral economics, the Sparse Max Consumer. So this is by a paper by Xavier Gabex, which is published in the Quarterly Journal of Econ, right? 2012. This is another of these top 5 papers. This paper, you know, as I learned about it when I was in grad school, right? I graduated, I actually entered in grad school around 2012, right? So right now, you know, this paper got published, and right now it's a big deal, right? So it's a really cool framework, very simple framework that allows you to understand these violations of rationality in a more systematic way. So basically, you know, there are a few models of behavioral econ that become very, very important, right? And, you know, a lot of them are about expected utility and choice over risk. But this one here actually has become substantially important, right, in these years. And now is, I would say, part of the canon. So yeah, we're going to study it now as a main chapter, right? Of course, it's not in Mass Colette. If you're interested, I can send you the paper. But again, you can also Google it. Here, the notes are your main resource for testing and so on, for tests. So have an hour and a half. I'm going to basically give you the introduction of the model, right? And then we're going to use it, hopefully, for the next class. So what is the idea? So we're going to consider a generalization of the rational model, right? Remember that the evidence I give you with the paper with Nael is not telling you, you know, that the model as this is going to work, right? That you have to take into account misperception of prices, right? So that gives you 2 possible potential channels. As Hursana said, maybe is that, you know, misperception doesn't matter and I just have to get rid of it, right? In the experiment, but maybe, you know, misperception actually is a fundamental part of how humans face the world. So, and that's why I also mentioned the frogs, right? So the frogs will have misperception always in the laboratory. So you will be never able to get rid of the misperception, right? There are frogs, right? They have limit brains. Humans, we are smarter than frogs, I hope, but I don't think there is an unlimited person, right? Maybe there is, right? Maybe there's someone there. But most of us, we have limits to our attention, right? I know a lot of you, you know, the class was kind of interesting, but then, you know, you just hire Netflix and then you're streaming some cool show, you know? No, hopefully not. But, you know, attention is scarce. And I think that's one of the issues that we have right now with Zoom and so on, right? So when you're in a class, you're forced to see the professor, and I can see all of your faces, and maybe you're snoozing or, you know, checking out your phone too much. I may actually, you know, do some face and then you reconnect, right? And then, you know, you don't want to be snoozing next to your classmate, right? Or snoring. Then, you know, you force yourself to put attention. And, you know, I think this is the single most important factor why teaching by Zoom is so hard, you know, getting engagement. is so hard because attention is this scarcer resource, right? And this is what marketing people know all along, right? That's why they bombard you when we had cable TV, right? Maybe you never had it, but you know, when you have cable TV, they spend so much on advertisement, you know, every minute after your show, because attention is scarce. They want to be on your mind. Now it's the same thing with ads on the you have these terrible web pages, you have to get ads, ad block, right? Because they want your attention. So attention is a scarcer thing. Amazon actually auctions these sponsor spaces on the search bar. Have you seen a sponsor, right? They are the main, one of the main sources of revenue, obviously, right? Because attention is scarce. Google auctions also the first things, you know, the suggested thing. So attention is obviously the scarce resource. And so let's have a model that actually has attention in it, right? So it seems obvious. Now it's not easy, but this guy Gavex, he's really smart, you know. He's also a nice guy, and you know, hopefully one day we can invite him to here. And then he created this model, which is very nice, as you will see. So okay, so this model basically allows us to include formally this reality that humans have limit perception. Okay, now we're not going to study like general misperception, right? Because that's too hard, maybe. But we're going to study misperception in prices. Okay, so this is this story of someone going to this experiment, right? And then you're given this budget line, and then I don't know exactly what the budget line is. So therefore, I kind of create a guess, right? And I'm going to use this perceived price instead of the true price. Example one. Example two, you are going to Costco, to Walmart, to Sobeys, whatever place you go, right? And then you go and start walking through the aisles and checking prices. Maybe you want to buy white bread, right? So which one do you buy? Well, many reasons, but among those reasons, you're going to see prices, most of you, right? So if you look at prices, are you going to look at the whole thing? Like $1.01, or you're going to kind of look to the first numbers, right? A lot depends on your rule. Everyone has a trick, right? And everyone's different, right? I'm really bad at looking at prices, so I almost see, is it above $2, $1? So take it, right? Easy. Go.
That's why they do 999 instead of 1,000, right? That's
exactly another thing. And there is a famous experiment by Chetty Croft that they did an experiment with taxes. So they basically run an experiment they went into a store, randomly pick goods, and then they give you the after-tax price in half of the goods at random, and then in the others they give you the price and the tax, so you could actually figure out yourself. What do you think will happen? So in the goods that give you the total price already added up, then people actually buy less of them because they actually internalize the full price, right? So we're going to try to understand this model as well, this issue with this model. Okay, so how do I do it? Well, obviously, utility maximization doesn't do it because it doesn't have perception. Okay, so we have to enhance the utility maximization by something else, and this is called an operator that is called the S-max optimization. So a sparse max operator. So what does the sparse do? I'm going to describe the algorithm, but now intuitively, it's going to take the highest object according to a utility, subject to the psychological budget, right? With an additional constraint, which is the part that Gavex worked hard on it, and we're going to think whether this is kind of the issue of this model that we have to think about. But the issue is that at the end of the day, right? So you misperceive prices. You go in Sobeys and you're looking at prices in the aisles of white bread, and then you still have $5 in your pocket, right? So then at the end of the day, you reach to the counter, and then you have to face reality. So you have to pay the actual prices, right? And then something happens. So you hit a reality barrier, right? So there, you have to hit the budget, you see? So this operator is going to make you maximize as if you were looking at the psychological price, while at the same time making you hit reality, okay? That's the challenge. Do you get it? Okay, so I'm going to describe the algorithm now. So let's say you want to use this sparse optimization model. And actually, I'm going to do it for the Cobb-Douglas. Let me see if I have. We can do it for the Cobb-Douglas in a second. Right now, I'm going to, I should have done it as I do for undergrads. But for grad school, I usually give you the theoretical part first. So, but yeah, nevertheless, let me go through the algorithm and then write the example, okay? Okay, so I need a Lagrangian, but this Lagrangian is going to be different. So I propose this sparse Lagrangian, which is basically going to be the following object. So the first thing is going to be that I augment the utility plus what it looks like a budget constraint. But I want you to notice what is the change here. So instead of the true price, what do you have here? You have the psychological price, okay? So for instance, imagine you have this experiment by Chetty, right? So you have the price of the good with tax, so that's $1.10, and the other is just the price of the good before tax, it's $1, okay? So here, the psychological price is gonna be without adding the tax. So for me, this is gonna be $1, right? While the real price is $1.10. Okay. Okay, good. So because of that, this is not a real Lagrangian. This optimization is, this lambda s here is not longer a variable. So it's not a Lagrange multiplier. This is just a positive variable that is gonna serve an adjustment later, okay? But this one here just maps the perceived, this utility that you have from expanding, right? And it maps to utility numbers. But this is not a Lagrangian anymore because this budget is fake. It only lives in your mind, okay? So mathematically, what I'm going to tell you is that lambda here is just a constant. So right now it's not a variable, it's a constant, okay? Got it? And here the budget, of course, has the fake price. Okay. So let's do it for the first. So what do you do with this case? So take the fake Lagrangian, and then take first order conditions. So then what do you obtain here? Is that this gradient of utility, so the marginal utility, is equal to the fake Lagrangian times the fake price. So in particular, I want you to do this this marginal rate of substitution, right? So the partial of good xi, right, by the partial of good xj, sorry, is equal to what? Psychological price of j, psychological price of I. Okay? So what this model is telling you is that you have the fake price, and then you do your marginal rate of substitution has to still be equal to the relative price of the fake price. So in particular, this is exactly what I think is happening in this experiment, right? So instead of looking at the correct ratio was, say, 1.3, right? But you think the ratio is 1 because you're rounding, okay? So here you're equating your marginal rate of transformation to 1, okay? So you're picking this exactly in the midpoint, while actually the true price was 1.3, the ratio. So therefore you shouldn't be on the midpoint, you should be a little bit above, right? So you're misoptimizing because you have the ratio wrong. Got it? Okay. But then, you know, the main issue of this model is that I have to still face reality. So that's the second part of the model. Okay. So the second part of the model says, look, I still have to hit the budget constraint. So I'm just going to simplify it, and I'm going to require that my demand is exactly at the budget line. Okay. Good. So what do I do? So from this first step for the first order conditions here, what I'm going to obtain is, of course, an X that is going to depend on the fake prices and on the constant lambda S, right? So in particular, this object here, the income doesn't matter, right? Because income at this stage is fake, right? So it's the fake budget, so you don't care about it. So the only thing that matters is the marginal rate of substitution and the ratio prices. So if you solve these inequalities, you're gonna obtain as an output of this step, you're gonna obtain X, a function X that depends on PS and depends on lambda S, right? So pretty much take this is a system of equations, right? And solve for x, okay? So solve the first order conditions above for x and obtain.
Victor, sorry. I kind of lost the big picture here. So we're trying to find the utility. We're trying to derive the utility.
To obtain a new demand. So I'm going to give you an example in a second. But okay. This demand is the demand you will have gotten if you have the wrong prices. Okay?
Okay. Right.
Yeah. So we're going to do it with a Cobb-Douglas. So if you give me one second, right? But in the end, the important thing here is that I have to go from this fake Lagrangian to income, and such that in a way that I'm able to hit the budget. So such that P times X of the fake demand, right, is equal to income. Okay? So what is the only degree of freedom I have here? Is the fake Lagrangian, right? So lambda S is the only thing, is actually a parameter. So this is the parameter I can calibrate in order for this fake demand to hit the income. Okay? Got it?
I have a question.
Yep.
Yeah, solving the first order condition, we do need one additional equation in order to get x, right?
Yeah, so you're gonna get 1 degree of freedom. That's why you're gonna get this lambda S freely going, right? So let me do the one with Cobb-Douglas, and then we can then go from it. Okay. So here, who remembers what is the rational Cobb-Douglas? The one that you have worked many times. What is the Cobb-Douglas demand for two goods? So for X1, right, of prices and income is equal to what? Is equal to alpha.
Alpha W.
W. P1.
P1.
Right? And now, what is the Sparse Max Cobb-Douglas? So it's going to be the following. I'm just going to give you the demand, and we're going to try to derive it using the algorithm. So it's actually alpha L, so in this case we have L goods, right? Times W, income, divided by the fake price. So this part looks like the rational demand, right? But the issue is that obviously this price is fake. So if I don't have any correction term, which is this object here, then if I go to the counter with my $5, right, I won't be able to hit the $5, right? So my budget line, I won't be choosing on the budget line. Got it? So then I need a correction term in order for me to be able to reach the Walras law. Okay? So you can verify it here. So what is the correction term? Is 1 over a summation over goods of alpha PL divided by PLS. So let's verify Walras law, right? So take PL, right? Multiply it by XL, right? And then you pretty much go here and multiply this PL here. The only term that is going to be affected by it is going to be this object here, right? So PL is going to be right here. And then this is a summation over goods, right? Over L. So the index is not working, so let me do it. This is issues with leaks. So I have to do it outside and copied and pasted it. So never mind. Now this is the summation over all goods, right? Now here I also take the summation over goods. Okay, so now what do I do? So do you recognize some pattern here? So you have alpha PL, PLS here with a summation, right? And here you also have PL, PLS, alpha. So you just rearrange terms, right? And you're gonna see that this is equal to income gets out of the equation, right? And here I have PL, right? and this is 1, right? So these two things cancel out, 1, right? And therefore this is equal to income. Okay, so now I want, before optimizing and doing the hard stuff, I want you just to see the new demand system. So the previous demand system was kind of very lame, right? Because imagine what is the budget share of the Cobb-Douglas. So multiply by prices, and therefore you have a constant budget share, right? So you always consume the same fraction of things. So you always consume 20% of food, 80% of non-food, right? Always, irrespective of prices. Now, this model is telling you, look, what happens if then sellers start changing your prices and then you misperceive these prices, right? Now you're going to see fluctuations around these constant shares, right? You see? Very sensible, right? So now, what is the nature of the fluctuations? Well, first of all, right, you're going to see that the fake price depends on the fake price, right? On the psychological price. So, and this is the part we haven't modeled yet. So the psychological price right now can be anything, right? So right now this model is too general because the psychological price is a free variable, right? Of what size? Of L size, right? So we started with how many parameters? Just alpha L, right? So L parameters. And now because of prices that are psychological prices, how many parameters do we have now? So we have pretty much a price, right? Is now this hidden object, right? Like a fixed effect of size L and changing per individual. So it's a huge number of parameters. So per individual is L more, okay? But in particular, you know, this model is way more richer because you don't have any more these constant shares. You have now fluctuations due to misperception, okay? But there are more things to do. So before going to further, right, we have the special case of PS is equal to P, and this is the rational case. So let's do now the optimization so you understand. So let's write down the Lagrangian, the fake Lagrangian. So this is the Cobb-Douglas. I'm going to write it here. Logarithm of x1 plus alpha 2 of the second one, right? Let me index it by L, so we have only two goods. Natural logarithm of x2, okay? And then here I put the fake Lagrangian and have income here, P1 fake x1 minus P2 fake x2, okay?
So this is the original utility maximization problem?
No, this is the first step of the Sparse Max. So we're doing
Sparse Max. Okay. Sparse Max, okay.
Okay, so now from this first step, what do? I get first order conditions, right? 2x. So as usual, this is alpha, right? x1 is equal to what? To lambda s p1, okay? And the same for the second good. So usually for rationality, what do you do here? You will take the ratios, right? But here, because you want to eliminate the lambda s. But here the lambda s is a parameter, so there is no budget, right? So instead of that, I'm gonna just take each condition and then solve for x1, okay? So here x1 is equal to what? To alpha. Here is 1 over lambda s.
Alpha 1, right?
And these are the fake prices, so nobody corrected me. That's the whole point, right? Fake prices. And this should be price 2, x2. Sorry, did someone say something?
Yeah, alpha 1 and alpha 2.
Yeah, thank you. Okay. And the same thing for x2. Okay. So do you get the object of the output of this algorithm, right? So this is a demand function that depends on the price, fake price, and on the lambda s. Got it? Now, what do I do with these objects? What was the step 2? So look for lambda s, right? Such that P1, real P1, multiplied by the object above, right? X1 fake price lambda s plus P2, the same object but with X2, is equal to W, okay? So just apply it, and therefore I have the following. So take this object here, this is X1, and multiply it by P1. And then here I have the second object, and multiply it by P2, okay? And this is equal to what? To income, okay? So what I'm looking for, lambda s, right? So lambda s factors out, is positive, goes to the other side, and then what do I get? I get 1W. So first of all, lambda s, right, is equal to what? To 1 over W of this index here that I already computed. Yep. That's it. Do you agree? Everyone is on this stage? So now, what is the final stage? I plug back lambda s on the demand XES lambda s to obtain the sparse maximizer demand function, right? XPW in terms of real price and real income. Got it? So I plug back in, and then of course the result is what I wrote before, so I'm not gonna do it again. Okay. So both things are equivalent because remember, this PS is right now is a constant, is a parameter. So you can kind of eliminate it. It's like condition the Cobb-Douglas on the alpha, right? Usually we don't do it. So as well here, it can be a function of the variables P and W, while PS is something fixed. So everyone now gets how the sparse max work.
I'm still a little bit confused about like, sorry.
Sure.
The sparse max itself, the Lagrangian sparse max, is that given from the data set, or is it something that you theorize, or where does that come from?
Where does the utility come from?
So you derive it from the data and then you rationalize it to make a utility function?
So two things, right? So it's a great question. So remember, a theory is basically creating latent object, imaginary objects to basically produce predictions, right, that you can test and observe.
Right.
So this is the lambda s, the PS right now are of the same nature as the utility function.
Okay.
Okay, they live in the
something
mind
you
of the
make up. Sorry.
Yes. Yeah, they live in the mind of the consumer, right?
Okay.
Then, of course, this has to be in some point a theoretical prediction. It has to be a theory of real life, right?
Right.
So
okay.
What is the output of this maximization? It's something in principle you can observe, because this demand here, right, is basically just a function of prices and income, right?
Right. Right.
Now I'm just gonna tell you the punchline. So remember the Zlowski matrix, because we're also ending the class, was symmetric for the rational case, right? Yeah. So if you compute for this new demand, the Zlowski matrix, it won't be symmetric, right?
Oh, because it's not rational.
Yeah. So that's the point, right? So this model is beyond rationality. It's going to be rational whenever the P psychological price is equal to the true price, in
Right.
which case all this term disappears and you're back to Cobb-Douglas. So this is a generalization of rationality. So of course, in the end, you will be able to test it with additional restrictions, right? Right now, the model is too general, as I said, because the psychological price is completely unrestricted, okay?
Mm-hmm. Mm-hmm.
So right now, on that line, I just want to give you a model of psychological price. And then, so again, the psychological price is like a utility function. So it's too general right now, right? So one particular way to go about it is to model it. So the same way the Cobb-Douglas is a particular case of the utility, right? So here, for instance, we can provide this model of psychological price, where you are a weighted average of what? Of the true price, and then of something called the default price. So the default price is you go to Costco, to Walmart, to Sobeys. I remember that the bread, the white bread loaf is $1, okay, $1. And then if I remember that, that's gonna be my default price, right? So then how do I process the new information? So say tomorrow this guy is mega promotion, so now it's 90 cents. So the price I'm gonna perceive is gonna be an average according to my perception parameter, ML, which is between 0 and 1. So if I'm fully rational, fully perceptive, I'm gonna be exactly knowing that the new price is 90 cents, right? But if I'm not, I'm gonna be halfway, right? Between $1 and 90 cents. Say tomorrow they increase the price instead to 120, right? And now my default is $1. So now with this parameter, say for instance, I have 1/2 is 0.5 is my attention parameter. So then what will be the psychological price? So it's the average of the two, right? So 110, you see? So this, so when M is equal to 1/2, you're just having an average. Else is a weighted average. If ML is equal to 1, you're rational because you exactly perceive the true price, right? If M is equal to 0, you never see the prices. So you are like this shopper that is always on a rush. So you go and you know more or less bread costs of $1, right? You go, you pick it, you don't never see the prices, right? So that will be a default price of always 1. And then you are fully inattentive. You never check the prices. Got it? Okay. So I'm gonna go over this model in a second, sorry, in the next class. But when I want you to tell you like the punchline is that if I take and construct a matrix, this go with the Cobb-Douglas of basically the diagonal of all these attention parameters. So remember there are L number of goods, attention parameters, 1 per good, right? So attention for bread, attention for meat, for produce, 1 per each good. If you have that and you put it in a diagonal matrix, then the Zlowski matrix is going to be the symmetric matrix multiplied by this diagonal matrix. So in other words, it's potentially non-symmetric where the M's are not 1, right? So this provides a very elegant deviation from rationality. So this
Victor,
is a
sorry to interrupt. It's 2:30. Just letting you know.
Yeah. So thanks. So I'm going to stop now sharing and stop the recording. So we're done with the class. And yeah, I'm going to stay here for questions.